In the first half of this video, we briefly introduce x and y axes that form the Cartesian xy plane and discuss coordinates of points with respect to the axes. The Cartesian plane is an incredibly useful device for using mathematics to analyse phenomena that occur in two-dimensional spatial settings. We go further in the second half of this video and introduce a third z-axis that allows us to model phenomena in three-dimensional spatial settings. You might have heard the expression thinking outside the square or thinking outside the box, or maybe the term lateral thinking, originally due to Edward de Bono, all of which are synonymous with creative or novel ways of thinking or viewing ideas or problems, utilising a completely new or different perspective. The 17th century mathematician and philosopher René Descartes was one of the most original thinkers in the history of mathematics. He literally thought laterally in many ways, and in particular to discover his remarkable invention, the Cartesian plane, the topic of this video. In Latin, his name was Renatus Cartesius, from which the adjective Cartesian is derived. We've discussed the real line in previous videos. Descartes imagined not just one, but two real lines, positioned in space so that they intersect at zero and are mutually perpendicular. What could be more lateral than that? The real line from left to right he called the x-axis. The real line up and down he called the y-axis. Think of the x-axis as horizontal and the y-axis as vertical. Notice how the axes are perpendicular to each other. The intersection point is called the origin, which we denote by O. O for origin and O also for 0. This is a special case of the following. Take any point at all on this diagram. We'll call this point P, and move down to the closest point on the x-axis, say A, and move across to the closest point on the y-axis, say B. Then the pair A, B forms what's called the coordinates of P. If you imagine this diagram extending infinitely to the right and left and up and down, you get what's called the Cartesian plane or the xy plane. Let's practice with some real points. So here's a copy of the xy plane with some points marked on the axes. And here are 3 points that we want to plot, P, Q and R. The point P has coordinates 2, 1. The point Q has coordinates 6, 4. And the point R has coordinates 6, 1. And you can see that they form the vertices of a right-angled triangle. You could ask, for example, for the length of the hypotenuse, h, say, and then use the theorem of Pythagoras. Remember, the square of the hypotenuse is the sum of the squares of the other sides of the right-angled triangle. As we move from P to R, we go from 2 to 6 on the x-axis, that's 4 units. As we go from R to Q, we move from 1 to 4 on the y-axis, that's 3 units. So the sum of the squares of the two sides of the triangle are 4 squared plus 3 squared, which is 5 squared. So h is equal to 5. This calculation is a special case of a more general result. If we have points P and Q in the xy plane, then the distance d between them is given by this formula. D is just the square root of the sum of the squares of the differences of the coordinates. The formula for D comes about, as before, by finding a right-angled triangle in the plane and using the theorem of Pythagoras. Now, we don't live in a flat world, we live in 3 dimensions, so you could ask, can we adapt Descartes' lateral thinking to include a third copy of the real line? Yes, we can think of the xy plane now as horizontal, like a tabletop in your kitchen or your dining room. And then we take a new copy of the real line, which we call the z-axis, that emanates out of the tabletop and moves up and down vertically. Again, we denote the origin by a big O, but now we have 3 zeros. So how do we model points in space? Here are the axes again, and I've got some point P suspended in space. Imagine it's sort of hovering over the tabletop, which is the xy plane. We drop down from P till we hit the xy plane at, say, the point Q. We move across to the x and y axes at the points say A and B, and we can move directly across horizontally to the z-axis at some point, say C. These numbers A, B and C form what's called the coordinates of P. Notice that the coordinates of Q are A, B and 0. Then we can ask, for example, what's the distance from P to the origin O? Call this distance D, say. Can you see Pythagoras lurking? The triangle OPQ is in fact a right-angled triangle. With hypotenuse D, one of the shorter side lengths is this vertical length C. The horizontal length we'll call H, say. But H is itself the hypotenuse of another right-angled triangle formed by O, Q, and the point A on the x-axis. The shorter side lengths of this triangle are A and B. So if we apply Pythagoras to that triangle that I've shaded grey that's lying horizontally, we get that h squared is a squared plus b squared. But if we apply Pythagoras to the other triangle, we see that d squared is h squared plus c squared, which is just a squared plus b squared plus c squared. And so we conclude that d is the square root of the sum of the squares of the coordinates of P. Thus we have the following result, that the distance from a point in space to the origin is just the square root of the sum of the squares of the coordinates. And this works regardless of whether the coordinates are positive, negative or 0. In the diagram I had everything so that the coordinates were positive, but the mathematics still works. Let's look at an example. Do you remember the unit square with side lengths 1 and diagonal the square root of 2? What if we were to consider a unit cube where the side lengths are all 1? Here's an example of a cube, and we can imagine all the side lengths are 1. And then we can ask, what's the length of the diagonal of the cube? That is, the distance from one corner to the opposite corner. Of course you can figure it out directly, but let's put it in the context of our discussion of coordinates of points in space. Let's position the cube so that the point furthest away is at the origin, and then the point closest to us has coordinates 1, 1, 1 because it's the unit cube. Call that point P, and then by our formula the distance from P to the origin is just the square root of the sum of the coordinates. If we draw in the diagonal D, then D is the square root of 3.